Right, here's a walkthrough for the Physics Combined Science paper. It's the foundation tier from 2022 and it's paper 2. You get 1 hour and 10 minutes and it's worth 60 marks. Question 1. This question is about electrical circuits. Draw one straight line from each circuit symbol to its description. So this is the switch, this is a battery, and this is a resistor. An LED is basically a diode D, I, O, and then it gives light off. Part B. Figure 1 shows a lamp in a circuit. The lamp is switched on. The current in the lamp is a flow of, current is a flow of electrons. Part 2. The current in the lamp is 0.21 amps, so that's I for current. Calculate the charge, so we're looking for Q, that's charge. That flows through the lamp in a time of 300 seconds. Use the equation and state the unit of charge. So we just pop the numbers in. So the current was 0.21 amps. Multiply that by the time, which has to be in seconds, which is 300. And that comes out as 63. And it's charge, so it's coulombs. Question 2. A teacher prepares some equipment to demonstrate electromagnetism. Figure 2 shows the equipment. The teacher wants to show that iron filings are picked up by the metal rod when the switch is closed, fall off the metal rod when the switch is open again. Suggest a suitable metal for the rod. Iron. Part 2. Give 2 reasons for your choice. Well, iron would become magnetised when the switch is on. So when the current's flowing. And it would be demagnetised when the switch was off and there's no current flowing. You wouldn't use steel because once it becomes magnetised, it stays magnetised. Iron can be made into a temporary magnet. Part B. A student's mobile phone has an app to measure a magnetic field. The student places the phone on a table and rotates the phone until it is pointing north. There are no magnets near to the phone. Figure 3 shows the display on the screen of the phone. So the numbers show the strength of the magnetic field and the pointer shows the direction. State why the strength of the magnetic field shown is not 0. So there's no magnets near the phone, but the Earth has got its own magnetic field anyway. So that's what it's detecting. The student places a magnet near to the phone on the table. Figure 4 shows the magnet and the new display on the screen. Right, well, the strength's gone up and the direction's changed. State 2 changes in the magnetic field measured by the phone from figure 3 to figure 4. So the strength increased and the direction changed. Part 3. Describe how the student could use the mobile phone to investigate the strength of the magnetic field at different distances from the magnet. Right, we'll just place a ruler in between the phone and the magnet, see what the strength is, measure the distance, then move the magnet and see what the strength goes to, and then compare how strong it was. Place the magnet near the phone. Use a ruler to measure the distance between the phone and the magnet. Record the strength of the magnetic field. Move the magnet and measure the new distance. Record the new magnetic field strength. Compare the results. You'll easily get 3 marks for that. Question 3A. An electric water pump is powered by the 230 volts main supply. That's the voltage. Figure 5 shows inside of the plug on the cable to the pump. One wire in the plug is the earth wire. The other 2 wires are, well, it's the live and the neutral, so that's B. Remember, the top pin is the earth. The live wire goes to the fuse, and the neutral wire is the other wire. That completes the circuit. Part 2. Describe the purpose of the component labelled X. So X is the fuse, and it's for safety. It blows if there's too much current. And it stops fires and overheating. Protects the user. So you'll definitely get 2 marks for that. Part B. The 230 volts main, so that's our voltage, supply transfers 9,000 joules of energy, so that's E for energy, to the pump motor in 1 minute. Right, that is 60 seconds, and that's our time. Calculate the current, so I equals our target in the pump motor, and use the equation. Right, they've even rearranged it for us, so I is the target, so we'll just need to pop the numbers in. 9,000 joules of energy divided by 230 volts times by 60 seconds, and that comes out as 0.65217. And I'll just round that down to 2 decimal places. 0.65 amps. Part C. The system transfers 8,400 joules of useful kinetic energy to the water passing through the pump in 1 minute. Figure 6 shows a diagram of the energy transfers. So 9,000 went in, 8,400 joules comes out as useful. Explain why the useful energy transfer to the water is different from the total energy supply to the pump. Well, we've got energy that gets wasted, and it'll be as heat to the surroundings. That's your standard answer when talking about energy transfers. Part 2. Calculate the efficiency of the pump. Use the equation. Useful energy transferred by the pump divided by total energy supplied to the pump. Let's have another little quick look. So make sure we get the numbers right. So the useful energy transferred by the pump was 8,400 joules, and the total energy in was 9,000 joules. And that comes out as 0.93 recurring. So 0.93. 93%. If they did want it converted to a percentage, remember, just multiply it by 100. Question 4. 3 students carry out an investigation to determine their powers when running upstairs. Part A. Figure 4 shows a diagram of the stairs with 4 distances A, B, C and D marked. The students need to calculate the work done against gravity. Which distance should be used in the calculation? Well, gravity acts vertically downward, so we're looking for a vertical height or vertical change in height. So that would be B. So the answer is B. Question B. They take turns to run up the stairs and use a stopwatch to measure the time taken. The students estimate their own weight. Estimate. Right, might have to come back to that. Figure 8 shows a table of their results. The table is not complete. State the unit for work done. Right, well, work done equals energy transferred, so that's in joules. J. Part 2. Use the data for student B to calculate his estimated weight. So weight here. Now weight is a force and they've gave us the distance and the work done. So work done equals force times by distance. So we'll have to rearrange that. So if you've got to use a magic triangle, F times by D would go on the bottom, F times by D and W, work done, goes on the top. Cover up what we're looking for. Well, his weight is the force, so cover up force. You've got to do the work done divided by the distance. So his weight, which is the force that he's lifting, it's work done divided by distance. So that's 1,960 joules divided by 4 metres. And that comes out as 490. And that'll be newtons, because it's his weight. Part 3. Use the data for student C to calculate the time she takes. Okay, so they've gave us the power P, time taken T, and the work done, which we said was W for work done before, or you could say it's E for energy transferred, because energy transferred equals work done. The equation we need is the power equals energy transferred divided by time taken. We need to rearrange that, so magic triangle, E goes on the top shelf out here, so it goes on the top shelf in there, and you've got P and T. Cover up what we're looking for, which is time, and what we're left with is E divided by P. So T equals E divided by P. Pop the numbers in. So her energy was 2040 joules. Divide that by her power, which was 425 watts. And that comes out as 4.8 seconds. Does that seem to fit in with the other values? Yes, it does. Part 4. Use the data for all 3 students to calculate the average power of the students. So we just need to add these 3 powers together and then divide it by 3. And that equals 433.6 recurrent. And they've done their powers to 0 decimal places, so we'll round that up to 434. Question C. Identify a significant source of error in the investigation and state how this error can be reduced. So let's go right the way back. The source of the error. Well, their weight was only an estimate. So that's the source of error. What should they do? Well, they should actually measure it with scales. Weight was only an estimate. Measure it with scales. Question 5, Part A. Figure 9 shows a lamp connected to a DC power supply. The power supply provides a potential difference, voltage, of 4.5 volts, so that's V. The current in the lamp is 0.3 amps, so that's I. Calculate the resistance, so R is our target. Use the equation. Right, they've even rearranged it for us, so we just need to put the numbers in. So that's 4.5 volts divided by 0.3 amps, and that comes out as 15 ohms. Part 2. Calculate the power supplied to the lamp. Well, the easiest way to get the power is the current times by the voltage. So the current was 0.3 amps and the voltage was 4.5 volts, and that comes out as 1.35 watts. Part B. Another identical lamp is added to the circuit as shown in figure 10. The power supply provided the same potential difference, so the same voltage, as it provided in the circuit in figure 9. State and explain the difference between the brightness of the lamp in figure 9 and the brightness of a lamp in figure 10. So figure 9 only had one bulb, so that got all of the voltage, so that'll be twice as bright. The voltage in this circuit has to get shared between two bulbs, so they'll be dimmer. And we can also say it because with more bulbs there's more resistance, so the current will be smaller. And we'll definitely get 3 marks for that. Part C. A student is given a low voltage power supply and a 1 metre of resistance wire. The student uses these and other pieces of equipment to measure the resistance of just 50 centimetres of the resistance wire. Draw a diagram of the circuit that the student should use. Your circuit diagram should identify the pieces of equipment that the student uses. Right, so let us draw the circuit for you. Ruler, power supply, ammeter, voltmeter, crocodile clip, and you only want to tap off 50 centimetres. You don't want to put that voltmeter across the full 1 metre. So that's where they're trying to catch you out. And obviously to get the resistance, it's Ohm's law rearranged, R equals V over I. So you knew that you were going to have to measure the voltage, and we do that with the voltmeter, and measure the current with an ammeter. Part D. Describe the difference between direct current DC and alternating current AC. So direct current, the current flows in one direction, and AC, alternating current, the current changes direction, goes backwards and forwards. Question 6, Part A. When water boils and turns into steam, there are changes in the arrangement of particles and the density. Which of these show the changes? So you're going from a liquid into a gas. So in a liquid the particles are quite close together. and they're randomly arranged. In a gas, they're randomly arranged, but they're further apart. So space between the particles in steam, well, the spaces are bigger than in water, so that could be true. That one says bigger than in water, that could be true. Smaller in water, the spaces are not smaller than water, they're bigger, so that's wrong and that's wrong. And the other thing is the density of steam. Well, the density is how much mass you've got per volume. So there's less mass in here in the same amount of volume. So the density is less than water. So your answer is B. Part B. Figure 11 shows some water in a measuring cylinder and a lump of iron. The lump of iron is lowered fully into the water. The water level in the measuring cylinder rises to 530. Right, so what's it on at the minute? 400, and each one of these, there's 10 little lines, so each one is 10, and there's 9 little lines, so that's 490, and that's centimetres cubed. So the change in volume equals, well, it went up to 530 from 490, so that is a change of 40 centimetres cubed. The density of iron is 7.9 grams per centimetre cubed. So that's good, that's already in centimetres cubed, and that's in centimetres cubed, so we don't need to convert anything. Calculate the mass, so mass is our target of the lump of iron. So we're going to need to rearrange this equation. So we'll do a magic triangle, top shelf, multiplied sign, mass goes on the top shelf, so that's M up there, and density and volume will go on the bottom. Now we want to work out mass, so we'll cover up mass. To get the mass, you need to do the density times by the volume. So mass equals density times by volume. That's the symbol for density. Let's put the numbers in. And that comes out as exactly 316. And that will be grams, because those centimetres cubed cancel out with those centimetres cubed and just leave the grams behind. And they want the answer in grams. 316. Part C. A piece of wood has a similar shape and volume to the lump of iron. The density of the wood is 0.82 grams per centimetre cubed. The density of water is 1 gram per centimetre cubed. Explain why the method used in part B cannot be used to determine the mass of the piece of wood. Right, well, the density of wood is less than the density of water. So wood won't sink in water. It'll float. So when you pop the wood in here, it won't fully displace its own volume because it'll be partially floating. Density of wood is less than the density of water. So wood will float in water and won't fully displace its own volume. In other words, volume will be incorrect. You can't measure the volume, if that's easier to see. Part D, the last question. It's our 6-mark question. A student needs to determine the specific heat capacity of water. Figure 12 shows some of the equipment the student uses. Low voltage heater and a beaker of water. Describe the method the student should use to determine the specific heat capacity of water. Your description should include, with reasons, what other equipment needed and the measurements needed. You may draw a diagram if it helps you answer. Right, well, as I say to my students, base your explanation on the calculation. So the calculation for specific heat capacity is the change in heat energy, delta Q, equals mass times by specific heat capacity times by the change in the temperature. Now if we rearrange that to find the specific heat capacity C, now our magic triangle will need 2 multiplied by signs, because there's 2 multiplied by signs here. And we've got M times by C times by delta theta. So we'll pop them in. And one space and one thing, so we'll pop that in, delta Q on the top. And we're looking for C, so we'll cover up C. And what we're left with is how to work it out. Delta Q divided by mass times by delta theta. And now the equation basically tells us what we need to measure, and we just say what we're going to measure it with. We need to measure the heat energy. With what? With a joule meter. We need to measure the change in temperature. With what? With a thermometer. We need to measure the mass of water. With what? With a balance. So we'll get 1 mark for that, 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 and 1 mark for the equation. Other equipment needed. You'd need a power supply. You'd need a joule meter to measure the energy. You've got the heater. That would need to go in the water. So beaker of water. Say that the heater needs to be fully submerged. You could put a little stirrer in the bottom. And you've got your thermometer. And you could even say put a lid on the top. And you could even say put insulation around the sides, if they wanted to know how to improve it. So you get extra mark for that, that, power supply, stirrer. I've saw sometimes they say how can you make it more efficient. That's what the stirrer, the lid and the insulation is for. So you'll definitely get your 6 marks by saying any of that. Well, I hope that's been useful. The more of these past papers you do, the better you get. Definitely. Very best of luck in your exams. Subscribe to the channel, smash the like button and work hard and be nice. Bye for now. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.